Space is not empty. It is filled with a stream of charged particles. We call this stream the solar wind. This wind originates from the sun. It constantly flows outward, shaping the environment of our solar system. Understanding solar wind is crucial. It affects our planet and our technology. The solar wind is a powerful force. It can disrupt satellites and communication systems. It also creates the beautiful auroras we see on Earth. The sun is a giant ball of hot gas. It is constantly releasing energy in the form of light and heat. This energy heats the sun's outer atmosphere, called the corona, to millions of degrees. At these extreme temperatures, the sun's gravity can no longer hold onto the particles. They escape into space, forming the solar wind. The solar wind is made up of mostly protons and electrons. These are charged particles that travel at incredible speeds. The speed of the solar wind varies. It can reach up to millions of miles per hour. This constant stream of particles carries the sun's magnetic field throughout the solar system. The solar wind is not uniform. It has different speeds and densities depending on the activity on the sun. When the sun is active, it releases bursts of energy called solar flares and coronal mass ejections. These events can significantly enhance the solar wind, creating what we call solar storms. The Earth is constantly bombarded by the solar wind. This stream of charged particles would be harmful to life on Earth if not for our planet's magnetic field. This field acts as a shield, deflecting most of the solar wind around our planet. The Earth's magnetic field is generated by the movement of molten iron in its core. This field extends far into space, forming a protective bubble called the magnetosphere. The magnetosphere deflects most of the solar wind, but some particles can still penetrate. When solar wind particles collide with atoms in Earth's upper atmosphere, they can excite these atoms, causing them to emit light. This is what creates the beautiful auroras, also known as the northern and southern lights. These dazzling displays of light are a testament to the power of the solar wind and the protection provided by Earth's magnetic field. However, during intense solar storms, the solar wind can compress the Earth's magnetosphere. This compression can disrupt satellites, communication systems, and even power grids on Earth. Understanding how the solar wind interacts with Earth's magnetic field is crucial for mitigating these potential risks. Just like we forecast the weather on Earth, scientists also forecast space weather. Space weather refers to the conditions in space that can affect Earth and our technology. The solar wind is a major driver of space weather. Scientists use a variety of instruments to monitor the sun and the solar wind. Ground-based telescopes observe the sun for solar flares and coronal mass ejections. Spacecraft, like the Solar and Heliospheric Observatory (SOHO) and the Parker Solar Probe, provide real-time data on the solar wind's speed, density, and magnetic field. By analyzing this data, scientists can predict when a solar storm might hit Earth. This information is crucial for satellite operators, who can then take measures to protect their spacecraft. Power grid operators can also adjust their systems to minimize the impact of geomagnetic storms caused by intense solar wind activity. Space weather forecasting is still a relatively new field. However, it is rapidly evolving as we become more reliant on technology that is vulnerable to space weather events. The goal is to improve our ability to predict and prepare for these events, ensuring the safety and reliability of our technological infrastructure. Section 5. Auroras, dancing lights of the sky. One of the most visible and captivating effects of the solar wind is the auroras. These mesmerizing displays of light occur when charged particles from the solar wind collide with atoms in Earth's upper atmosphere. The auroras are most commonly seen in the polar regions where Earth's magnetic field lines converge. When solar wind particles are funneled down these field lines, they collide with oxygen and nitrogen atoms in the atmosphere. These collisions excite the atoms, causing them to emit light. The color of the aurora depends on the type of atom that is excited. Oxygen emits green and red light, while nitrogen emits blue and purple light. The combination of these colors creates the stunning and ever-changing displays that we see in the night sky. Auroras are not just beautiful phenomena, they are also a reminder of the constant interaction between the sun and Earth. By studying auroras, scientists can learn more about the solar wind, Earth's magnetic field, and the dynamics of our upper atmosphere. Section 6. solar storms and technological impacts. While the solar wind is a constant phenomenon, its intensity can vary significantly. During periods of high solar activity, the sun can release bursts of energy called solar flares and coronal mass ejections. These events can enhance the solar wind, creating solar storms. Solar storms can have significant impacts on our technology. The charged particles from these storms can disrupt satellites, causing communication outages and GPS errors. They can also induce currents in power grids, potentially leading to blackouts. One of the most famous examples of a solar storm's impact occurred in 1989. A powerful coronal mass ejection struck Earth, causing a major blackout in Quebec, Canada. The storm disrupted the power grid, leaving millions of people without electricity for hours. As we become more reliant on technology, the potential impacts of solar storms become more significant. Understanding and predicting these events is crucial for mitigating their risks and ensuring the resilience of our technological infrastructure. Section 7. Studying the solar wind. Scientists use a variety of methods to study the solar wind. Ground-based telescopes observe the sun for solar flares and coronal mass ejections. Spacecraft provide in-situ measurements of the solar wind's properties. One of the most important tools for studying the solar wind is spacecraft. These spacecraft carry instruments that can measure the speed, density, temperature, and magnetic field of the solar wind. By analyzing this data, scientists can track solar storms and study the long-term behavior of the solar wind. The Parker Solar Probe, launched in 2018, is a groundbreaking mission to study the solar wind. This spacecraft is designed to fly closer to the sun than any previous mission, allowing scientists to study the solar wind in its most pristine form. By studying the solar wind, scientists hope to answer fundamental questions about the sun and its influence on the solar system. This knowledge is essential for understanding space weather and its potential impacts on Earth. Section 8. Solar sails, riding the cosmic winds. The solar wind is not just a force to be reckoned with, it also offers a potential source of propulsion for spacecraft. Scientists are exploring the concept of solar sails, which would harness the momentum of the solar wind to propel spacecraft through space. Solar sails are large reflective sheets that are unfurled in space. When photons from the sun strike the sail, they transfer their momentum to the sail, pushing it forward. The solar wind, though less dense than sunlight, can also exert pressure on the sail, providing additional thrust. Solar sails offer several advantages over traditional chemical rockets. They do not require any propellant, which significantly reduces the weight and cost of spacecraft. They can also operate continuously, allowing for long-duration missions to distant destinations. While solar sail technology is still in its early stages of development, it holds great promise for the future of space exploration. Solar sails could enable missions to the outer solar system and beyond, opening up new frontiers of scientific discovery. Section 9. The future of solar wind research. The study of the solar wind is a dynamic and evolving field. As we continue to explore space and rely on technology that is vulnerable to space weather, understanding the solar wind becomes increasingly important. Future research will focus on improving our ability to predict solar storms and their potential impacts. Scientists are developing more sophisticated models of the sun and the solar wind, which will allow for more accurate space weather forecasts. New missions are also being planned to study the solar wind in greater detail. These missions will provide unprecedented insights into the origin, evolution, and behavior of this fundamental component of our solar system. The study of the solar wind is not just about protecting our technology, it is also about unraveling the mysteries of the sun and its influence on the solar system. By understanding the solar wind, we gain a deeper appreciation for our place in the cosmos and the interconnectedness of all things in the universe.